So in this video, statistical power number 2, the second video, we're actually going to define power. So in the first video we didn't even get to the definition of power, but here we will talk about it. Okay, so here we are, and we have our two distributions plotted on here on this axis, and so this is the normal population distribution of the people who have not taken the drug, okay? And then this is the alternate population distribution of the people who have taken the drug. And just remembering that this is in the real world. This is the actual distribution. As researchers, we do not know this. We are trying to guess this. And so we're doing our hypothesis test by taking a sample, and in this case we're taking a sample here of n equals 25, okay, from the population of people that took the drug. But we as researchers do not know whether these distributions are different, okay? So just to explain power and error, we need to show you what the real world is like, but in reality we don't actually know that. So these are the distributions, and as we talked about before, we basically in hypothesis testing only work with the null hypothesis distribution, right? So we make an assumption about that distribution, so we know that that distribution has a mean of 500 and standard deviation of 100. And so using that information, we set a criterial value here, which we did in the last video, so we know. And this value is where we are going to reject the null hypothesis. So when we do our sample, we we're not aware yet of this alternate distribution over here, but we take our sample of 25 and we get a score, and this value is 533. So we get a score, and then we, based on that mean of the sample that we took, we decide whether to reject the null hypothesis or not. And so what we said is that the alpha level, the alpha, is the part of this null distribution that goes beyond the criterion for rejecting the null. And the region beta is the region over here where the alternate hypothesis distribution is below this critical value here of 533. Okay, so we already talked about that. So this is beta and this is alpha, and then we could just go over here and we remember that the type 1 error is alpha, and that's the probability of rejecting the null even if the null is true. So here we see that that probability is in here. So we're going to reject the null if the score of our sample is over 533, but there's still a possibility that that sample did come from the null distribution, right? And it's this probability, which is defined as alpha. And then the probability that there is some likelihood of accepting the null hypothesis even though the alternate hypothesis is true, which is beta. And then that is right here. So we would accept the null because this mean of the sample would have come under 533, so we'd accept the null. But it could have come from the alternate hypothesis distribution, right? Because this is the alternate hypothesis distribution. So there's not a high probability, but there's some probability, so that's beta. Now, what is power? Power is 1 minus beta, as we say over here, okay? And so power, we know that the whole total distribution adds up to 1, and so what 1 minus beta is actually going to be this whole portion here. So 1 minus beta then is this probability. So it's the probability of accurately accepting the null hypothesis. Accurately rejecting the null hypothesis. So it's the probability that you have an actual effect when your study says you have an actual effect. So it's the portion, so you can see that it's 1 minus beta, and beta is the proportion of that alternate distribution that falls below the critical value. So to calculate power, you need to know a number of different things, and that is what we will talk about now. So now we know what power is, and now what we're going to talk about are the 4 interrelated components of power. And all of these things are things that impact power, and if you know 3 out of the 4, then you can calculate power. So now we're going to talk about the 4 interrelated components of power, and you can use a mnemonic bean for to remember these 4 different components of power. So the first component is B, and that's beta. That stands for beta. So we see obviously that the beta, which is right here in the red, so the beta is the type 2 error, as we discussed before, and it's the portion of the alternate hypothesis distribution that falls under the critical value that was defined for the null hypothesis, for rejecting the null hypothesis. Okay, so that's beta. Obviously that plays that's one of the features, the things that's determining power, because power is 1 minus beta. And the second component of power is E, and that stands for effect size. So effect size is the difference between the means of the different sampling distributions. So here we can show that the effect size is basically this difference. And officially, the effect size is, let's see over here, it's often written as D for difference, excuse the alarms here, between mean 1 and mean 2, the 2 different means, the 2 distributions, divided by the sigma, or standard deviation. So that's just a normalized number, right? So these are really normal distributions that that are made up of z-scores. So this is the effect size sort of in z-score terms. So it's just the distance between the 2 peaks of each distribution, and that's effect size. So obviously, if you move one of these distributions over, the power, if you move the alternate distribution over, so the distance between the 2 distributions is larger, then your power, which is this section, the part of the alternate distribution that falls above the critical value for rejecting the null, that is going to increase, right? So the difference between the 2 means, the bigger the difference, the more power you have. The less the difference between those means, the less power you have. So here's an example. We can compare these two. So in this one, the difference between these means is pretty bigger, sort of like the one up here. And so you can see that, so the critical value is going to be over here, just the cutoff where alpha is 0.05, or whatever you define alpha to be. And so then whatever part of the alternate distribution falls on the right of that alpha, that critical value defined by alpha, that's the power, okay? And so over here, you can see here's a teeny difference between the means. So they still are different. These are different distributions, okay? So so in a way, it's not appropriate to reject the null. I mean, it's not appropriate to accept the null hypothesis if you get a sample from this alternate distribution, but the power of the test is small because here's the critical value here, and then the power is whatever part of the alternate distribution is falling over here. And so you can see that that's much less power on the right here than it is on the left. So here's power over here. It's much bigger. So what this means is that if you, so in both cases, the null, we should reject the null hypothesis because the sample came from this alternate distribution. If the effect, the difference between the means of those distributions is really big, you are less likely to make a type 2 error. So beta is smaller, therefore power is bigger. Over here, if the difference is teeny, beta is really big. So almost half the time here, your sample mean is going to fall under the critical value for the null hypothesis, and you're going to accept the null hypothesis. So this is all beta, type 2 error. And then the power is a lot lower here because beta is bigger on this side. So that's the relationship between the effect size and power. So I'm going to stop there because this is getting a little long, but the next two components of power are the A and the N, and those are the two that we're going to talk about. This is alpha, and N is sample size. And so those we're going to talk about in the next video. Okay, so see you in the next video.